FLOPS. What are they? Why are they so important in AI? And what does this have to do with training costs? In this video, we're going to answer that question, and we'll actually count up all the flops inside a large language model using spreadsheets are all you need. Stay tuned. If you're just joining us, I'm Ishan. I'm an AI consultant and educator, best known for implementing an early ancestor of ChatGPT entirely in pure Excel and vanilla JavaScript. We use simple tools like that to explain how large language models will actually work on the inside. You can go to the website, spreadsheets-are-all-you-need.ai, and subscribe to the mailing list to learn more. Okay, so what is a flop? Flop just stands for floating point operation. So you take the FL in floating point, the OP in operation, you put it together, and you get flop. Anytime you're adding, subtracting, multiplying, dividing, or other mathematical operation with what you might know as decimals, you're doing a flop. So if I do 5.2 plus 6.4, we just did a flop right there. Now, what might be a little confusing is when you add an S, and we're talking about flops. Confusingly, flops with a lowercase s is different than flops with a capital S. So flops with a lowercase s means more than one flop. Flops with a capital S is flops per second. By analogy, if you're thinking, say, in terms of miles, this would be like miles, and this would be like miles per hour. It's a rate. And you can actually see a little bit of this when you look at the Wikipedia page for flops. And you'll notice the formula for flops right here has flops with a lowercase s as part of the calculation. That's simply because if you want to know how many flops per second are happening, you need to know how many plural flops are happening in a certain time period. Now, we should probably take a step back and explain why flops even matter at all in AI. You've probably heard that large language models have been trained to complete sentences like this one. Mike is quick, he moves. And as a human, you know a reasonable completion would be he moves quickly, or he moves fast, or he moves around. But how do we get a computer to do that? Here's a fill in the blank that I think you'll have no trouble believing a computer can do. 2 plus 2 equals 4. It's a math problem. And we can make these math problems really complex using lots of floating point numbers, and computers are still good at them. In effect, what researchers have figured out how to do is take what is nominally a word problem, a fill in the blank problem, and convert it to a math problem. They do this by converting each of the words or tokens in your input into numbers. In this case, I've simplified it by drawing a single number, but in most cases, it's going to be a long list of numbers. Then what our AI or large language model will do is it'll do a lot of complex math. This is where you might have heard of terms like multi-head attention or multi-layer perceptron. At the end result of all that math, which is not as simple as just arithmetic as I've drawn here, you'll end up with a number. Technically, you're going to end up with a large list of numbers. And we'll look at that number and we'll do the reverse of what we did at the beginning, where we mapped words into numbers. Now we're going to map this number back into a word. And of course, the final number we get doesn't cleanly map to every single word we know of. So we'll look through our dictionary of number to words, and we'll notice that some are a little closer. So here, for example, quickly is very close. Fast is also reasonably close, but so is like and around. And what we'll do is we'll take words that are closest to this 233.5, and we'll give them a higher probability. So here we might give quickly a 43% probability, but fast we'll get a 19% probability to recognize that it's further away from the number that the model predicted. The key point in all of this is that the entire operation of the model is mostly math. This is not how most programs are built. Most traditional software programs are a series of logic, of flow control statements like you see here on the right. That means if we want to understand how big a model is or how fast it takes to run a model, all we need to know is all the number of calculations that are going to happen here on the left. Now you can actually see this inside Spreadsheets Are All You Need. This is the Excel file that I built that re-implements GPT-2 entirely in Excel functions. So here at this tab, type prompt here, you obviously have text. But once you get into the heart of the model, that's these block underscore tabs, block underscore 0, block underscore 1, and so forth, you'll notice if you scroll through this, it's almost entirely math, because the entire operation is really a bunch of flops. Now, let me show you this a little more clearly and precisely. We're going to use the JavaScript version of Spreadsheets Are All You Need to count the flops inside GPT-2 Small. And the way we're going to do that is we're going to go to spreadsheets-are-all-you-need.ai/GPT2 if you want to follow along. You're going to want to load the model parameters. The steps for doing that are in the video at the top of the page. I'm going to assume you've done that. And what we're going to do is profile really just two functions. The first one is matrix add. We're going to pretend there's a variable called flop count, and we're going to increment it wherever we see a mathematical flop operation. There's only 3 places we really need to focus on. Here's one of them, right in the matrix add operation. You can see there's 2 numbers being added right here and here. So we're just going to say window dot flop count plus. And matrix add actually implements 2 forms of matrix addition, the one you probably know and the one with broadcasting as they refer to it. So we're going to go here. Here's the other one. So we'll do that count right there, window dot flop count plus plus. Okay, next we'll go to matrix multiply. That's the other key place we need to pay attention to. And you can see the operation is right here. And you'll notice it's actually 2 operations. There's a addition plus equals and then a multiplication. So what we need to do is we need to take window and flop count and we need to increment it by 2. And there we've basically profiled the key flops we need to worry about. I'll get to the other ones in a little bit and why they're not as important. But now to actually do the measurement, there's only 2 things left to do. First, we have to initialize this flop count variable. And I happen to know a good place to hook into that. And I'll get out of this text editor and go to separate. There we go, into words. This is at the beginning of the parsing of the input prompt, and I happen to know that gets run once at the beginning. So it's a good place to hook in and just set this variable flop count equals to 0. Okay, and then the last thing we need to do is output our result. So to do that, let's go to where the predicted token is displayed. Right here. We'll scroll down. The flop count here, and then window dot flop count. Okay, now what we have to do is run it. Now I'm going to hit this run button. And I want to warn you that this is an educational tool, so it's not designed for use in production. I'm going to speed up this part of the video, and I'll join you at the end so you can see how the flop count turned out. Okay, here's our flop count. It's basically about 1 billion floating point operations in order to compute the next token when we've got 6 tokens in the input prompt. Now, there's actually a bunch of different ways to calculate this. I only focused on the matrix add and matrix multiply. I have done the work of actually profiling every single operation, and this is still a pretty close estimate. If you're really interested, I'll do another video where I go through all the relevant functions. Just let me know in the comments. There's 2 other ways that we can estimate the flop count for a model. The first is there's a function called fvcore if you're in PyTorch. That's what you've got here. You just give it a model, you run it, and then you can ask it for a flop count analysis. One warning though is it's actually going to give you the fused multiply and add. That's what you see here. That's why it's 5 times 10 to the 8th. And if you go here, that means you need to multiply it times 2 because it represents both a multiply and add together. So if you take the number they gave us and you multiply times 2, you get this, which is still pretty close. There's yet another way to do this estimate, which is a back of the thumb, rule of thumb, I should say, calculation. So this is the OpenAI neural scaling laws paper. And they give this estimate, which you could drive yourself if you go through the size of all the different parameters and matrices inside the model. But the key thing here is the forward pass of the model is basically, which is what we just did, 2 times n plus this other quantity. This turns out to be not as important. This basically means the number of flops you need per token is simply 2 times the number of parameters in the model, and that is how many flops need to be done for every single token that you inference on in the model. And to understand why this is, just go back to what a neural network is. A neural network basically is this analogy to a biological neuron and takes a bunch of inputs, it multiplies that times some weights, and then it puts it through some activation function. So the key operation that happens the most inside the model is this neural calculation. And it is simply, for every single weight here, there's a multiply right here, and then an addition. So basically, for every single weight, there's 2 operations you're going to do, a multiply and then an addition. And it turns out this dominates most of the calculation or flops that happen inside the model. So let's see how this rule of thumb measures up to our empirical measurement of the number of flops. The way the formula works is it's 2 times the number of tokens times the number of parameters. In our example, we were using Mike is quick, period, he moves. That's 6 tokens. I happen to know each of those words just maps to a single token. And then the number of non-embedding parameters inside GPT-2 small is about 85 million, as you can see here. And so then we just simply take 85 million times 6 times 2, and we end up with basically this, which matches about 90% or 93% close to the empirically measured number of flops. The key thing in all of this that I'm trying to illustrate is that the amount of processing the model does is fixed by the number of tokens. Took this example here and you rerun it with any other 6 tokens, you can just make it 1, 2, 3, 4, 5, 6. You will get the exact same number here. The amount of processing is fixed by the number of tokens, which is also fixed by the number and layout of the parameters, which we can estimate pretty well with this rule of thumb. So the key thing is that once we know the number of parameters, and we know the number of tokens it was processing or it was trained on, and we know the chips it was running on, we can make a decent estimate as to how long it took to train that model, as well as its potential training costs. Let's see that with the infamous example of DeepSeek. Okay, so let's use what we've learned to estimate DeepSeek. One thing you should know is when we did our earlier estimate, we did this rule of thumb, number of parameters times number of tokens times 2. That's for inference. That's when you're predicting the next token. When you're actually doing training, it changes slightly, and you're going to just have to trust me on it. The rule of thumb estimate is 6 times the number of parameters times the number of tokens. Okay, with that out of the way, let's go take a look at the paper itself and get some numbers out. So here is the DeepSeek technical report. And the first thing we want to go to is the number of parameters. Now, the number of total parameters is 671 billion, but we only want the active parameters because this is a mixture of experts. So that's 37 billion right here. So let's put that into our spreadsheet. So 37 e to the 9. And then we want the number of training tokens. So the number of training tokens is given right here, 14.8 trillion. So let's use that. 14.8 e to the 12. Okay, and then the claimed training time. So they have a table here. I'm only going to focus on this part right here, which is the pre-training part. That's 2664,000. So let's take a look at that. Equals 2664 times 1,000. Okay, and then to estimate costs, they simply used $2 per GPU hour. So we're going to put that in here. And then this gets you their training cost. So let's just do training cost here, which is this times this, which they claim is 5.3 million right here. So that's just a simple hours times dollars calculation. Okay, next let's take a look at the GPUs. They were using H800 GPUs right here. That's very similar to an H100 GPU. And you can go to the NVIDIA datasheet, which I pulled up right here, and you can look at the number of flops that it takes. Now, the number of floating point operations a GPU can use or do a certain amount of time depends on the size of the floating point numbers. In the case of DeepSeek, they're using FP8, but these numbers here are with sparsity. That's this note right there. And that's not the number we want to use. What we want to use is the number that's half that, which is 1979. So we're going to do 1979 e to the 12th. So for teraflops. Okay, now let's estimate how many flops total, floating point operations, were needed to do the entire, what they call pre-training phase of the model. That is simply 6 times the number of parameters, which we have up here, times the number of tokens, which we have right here. Okay, that's our number. Now we're going to see how long did it take the GPUs to crunch through that. If you take the total amount of floating point operations, let's fix this. This is flops with a lowercase s because it's the number of total flops it took. So we're going to take the amount of training time is this times the flops per second divided by the flops per second of the GPUs. and that'll give us the total number of GPU seconds that were done during training, and then the number of GPU hours. And we're doing that simply because they gave us the claimed training time right here in terms of hours. So we'll do this divided by 60 seconds in a minute and 60 minutes in an hour. And we get basically 461,000 GPU hours. Now they claimed more than that. They claimed basically, if you see here, about 2.6 million GPU hours. And that's because no one ever gets 100% utilization. So let's find out what what's known as the model flop utilization is, which is how close they got to the theoretical performance. The claim training time was right here, and that's the 2664K that they gave us. So we'll just take this and we will divide it by how long it actually took them. So how much it theoretically was supposed to take divided by how long it actually took. And we get about a 17% model flop utilization. Now, you may not know what a decent MFU or model flop utilization is. I've never trained a large frontier class model myself, but I went and I asked ChatGPT's deep research, which you haven't tried it, is amazing and awesome. Definitely recommend trying it out. It's addictive. And I just asked it for some variations on, go look at a bunch of papers, find out what researchers have reported for typical MFU. And it basically said between 20% to 50%. I think flash attention to, actually, it's missing that number is up above 70% or more. But 17.31% does seem actually reasonable for model flop utilization. So this 5.3 million number does seem legitimate. However, I think the number needs to be put in context. Do not do what is done in this article. And I'm going to cover up the URL bar to protect the guilty, but where it says DeepSeek trains its model for about 2 months at a cost of 5.6 million. By contrast, OpenAI is thought to have spent about 5 billion on development in the last year. This is, I cannot begin to tell you, apples and oranges comparison. In fact, DeepSeek themselves even say, this is just the cost of the final official training run. It excludes the costs associated with prior research, experiments on architectures, algorithms, and data. It doesn't include the people costs. There's so many costs it does not include. The analogy I like to give is it's a little like measuring the cost of a house by only the amount of timber that went into it, not counting everything else, including the services and all the people that went into putting the house together. Yes, it's a line item. Yes, it's one of the major line items you'd think of, but it so does not account for so many different things. Plus, this is the cost of just one run for one model. That is not comparable to a company that is training multiple models and on multiple runs. It is so apples to oranges comparison. Do not try and even equate these numbers. Another thing it doesn't capture is the amount of work it takes when you're at the frontier of science. And the example I like to give is Thomas Edison, right? The famous thing they often say apocryphally is he tried 10,000 or he tried 1,000 different attempts at the light bulb before he came up with it. Somebody actually looked, and this was the most reliable number I was able to find, and it was basically 2,000 times, nearly 3,000 times actually. Those 3,000 attempts came with a cost, right? So like Thomas Edison could not take the 3,000th light bulb that he built and look at the cost to just make that one light bulb at the end and say, oh, that's how much it cost me to invent this thing. No, there was basically 2,700 other failed attempts that cost money before he actually hit on the one that worked. And this is like the experiments they have to do, ablation experiments, when they're basically building a frontier class model. So it's not comparable. The other thing that's worth noting is this article from Dario Amodei, who's the CEO and co-founder of Anthropic, another frontier model training company. And he makes a really interesting point that the cost of building models is following a certain curve where it comes down. And so his statement is that they produce a model close to the performance of US models that are 7 to 10 months older, because the models we're using today were trained a while ago and for a good deal less, but not anywhere near the ratios that people have suggested. And he offers some rough guidelines for how much it cost Anthropic that you can compare them. And it's not this 5 billion. So to sum up this video, hopefully you now have an understanding of what flops are, why we can use flops to figure out the cost to run or train a model, and then also be able to put that number into context and know that it's just one line item and not the whole kit and caboodle in terms of building a model. So was this video a flop? Let me know in the comments. I learn from human feedback just like your favorite reinforcement learning tuned AI model. So drop that RLHF in the comments and I will see you in the next one. Thank you.